being part of our event. My name is Cale Harbor with Advanced Control Solutions, and along with our sister companies, Olympus Controls and Gibson Engineering, we make up the Applied Automation Group. It's our pleasure to have with us today Raj from Tessella Tech with us. Tessella Tech has been a great innovator in supporting robotic work cells with a great resource for modular and adaptable robot tables, inserts, and other devices to be able to help build and outfit a robot cell to let you achieve that next level of production and be able to make it easy to swap over one product to the next. So that being said, I'm going to pass this off to Raj and take it away.
Actually, it's going to be Danny, so who's going to be presenting with the system, Cale?
Oh, yeah. Okay. My pardon. Danny?
So, fantastic. So thanks for having us, Cale. We really appreciate the opportunity, everyone at the Tessella Automation. Are you able to see what's on the screen?
Yes, everything good.
Great, great, awesome. So Tessella Automations, we are going to be discussing an automation solution, glue dispense. And let's see here. Just a little bit about us. We're a tech company founded in Silicon Valley by roboticists and visionaries, and we're looking to create products to help accelerate development and deployment of automation and robotics designs and solutions. I have everyone here, just shows you the years that we've been in business and pretty much gives you an idea of how old we are. For glue dispense and any other type of application dealing with automation robotics, so Tessella, what we wanted to do is, how can we provide enabling technology to automation? We didn't want to just be a Me Too company, but we have a background of automation for years, and we're looking to solve problems and create solutions. So one of them was, how do we accelerate development time of automation projects from design to an actual workable machine? The problem that we see today is a typical automation or robotic tool. It's designed for dedication and permanence for a specific task or application. This can be good for high volume, low mix applications, but it's not necessarily efficient for high mix, low volume applications. So the solution that we saw was to design an adaptable machine or adaptable machines which are flexible and modular at its core. It can be configured or reconfigured during prototype and or during production phases. The platform can also be reused at the next generation application. The second problem that we saw was robot setup and calibration. The time to do that is consuming. So what we thought to do was create a precision platform to go with a precision robot. So precision platform, precision modules for a precision robot to create positional stability and repeatability. The way we approach applications, or us engineers that do applications, we have a set of design fors. So there's a whole list of it. Today we're going to focus just on simulate everything before you build anything, and data for positioning. So the application that we're discussing is glue dispense. How do we get from concept and design to a working tool? And you see that little clock up there with flames behind it. How can we do this quickly? Glue dispense is nothing new. It's not the glue dispense so much that we're focusing on, but it's the process to get from the concept and the design to a working tool. We utilize an application software, an application simulation software that allows us to do concept and development and proving out concepts before we actually put the product, start cutting metal. So what we've done is we use a software called RoboDK. I'm not trying to push their software, but it is something that we've found that's a simulation software that helps us to create the architecture. So what we do is our product that we have is a precision platform and precision modules. I'll show you that here in a second. But what we do is we upload these precision platforms and precision modules into the simulation software. We upload the fixturing. We also upload the parts that we are going to be doing something with, or that we're gearing the application toward. We create the architecture, we simulate it. So we actually build out the application ahead of time, so that we can look at process flows, we can look at cycle times, and then we can run that through a live simulation. And then once we're satisfied, we can kind of lock down the design. The products that we load up in there is, now we talked about precision platform. So for us who design robotic cells, if you've ever had to calibrate a robot, you know it can be very painful. You adjust one degree in this angle, it throws off all of your reach, and it throws off your position. So we created a three-dimensional surface, and these are the structural features on the surface. The main base for this specific application is a 600 by 600. The nest size is about 150 by 150, and it's very stiff. So this is actually not by 100, but it's by 6 millimeters. It's very stiff, meaning that the deflection from 0 to 600 is very minimal. It is a low mass, 85 pounds. I mean, it will take 2 people to lift it, but the weight also acts as a ballast for the inertia that the table might see due to the robot. It's a high precision finished structure, or repeatability. And when I say repeatability, this is actually the plates that we put down onto the table itself, and you can see those plates there. When we position those based on the dowel pins that are sitting in there, we get a 30 to 60 micron repeatability. Now I am buffering the accuracy on that. I've seen it get down to about 20 microns. So it's self-fixturing with precision dowel pins, and the straightness and flatness is 100 microns over 600 millimeters. Now, to couple with that table, we do have configurable drop-in modules. These modules, there you have some that are partially configured. We have a lift and locate there. We have one with a Cognex barcode. We also have the one that you see there on the bottom right is a robot plate that's specially configured for a mecha robot, so that we can position the robot on the table. Then we have fully configured modules. The table can utilize different types of robots. So you see there, you've got a 6-axis robot. You can put a Cartesian on it. You can put a scalar on it. With that, I'll move over to the camera here. Or actually, let me move over to the simulation software. The simulation software here is the aid that we use to do the concept and development. So as I had mentioned, we have uploaded the plates. These are blank plates. These are off-the-shelf blank plates that we use to kind of cover this surface. The surface is a 3x3 here, 600 by 600. We formed the application by first saying, okay, well, we need to have an infeed. So we created, on this plate, we created an infeed for our parts. Then from there, we want to take the first, this is a bottom case, and that bottom case is paired up with a PCB board. Now this is a PCB board in this area right here. Let's see, 1, 2, 3, 4, 5. This is position 7. So position 7, we created a simulation tool. The simulation, and then it simulates into position 8 here. This is position 8. Again, all these are identical. These, this is a tessellated surface. So the geometric figure that you see here, the square 150 by 150, is identical. So this one here is a more of like a grid style plate. So we 3D printed the holder for the simulator and then mounted it on this grid plate. For the fixture, we did the same thing. We 3D printed the fixture that holds the bottom case, and then we created a holder for the glue dispense. Now, the glue dispense, you can see it actually goes below the headline of the table. And so this is what we call 3D, three-dimensional. So we're not just working with a top surface, we're also working with the bottom surface too. So you can actually work underneath. Now, once we form the application, we can look at the flow. So we can see the robot's moving to position 4. It's going to pick up the bottom case. It's going to position that into the fixture. We place it into the fixture, then we rotate about. We grab the PCB board there, and then we're going to rotate in, and we're going to place it in. There, it's locked into position. Now we're going to dispense the glue. So we pick up the glue from position 9, and then we make the move. So all this was done in this simulation software. So this really helps us to form the application, and it accelerates the concept and development stage so that we can move quickly we can kind of compress the engineering time. From there, once we've configured it, we're actually going to take our parts and put them together. So if you look here, this is the system. The system here is comprised of a tabletop that you see here. This is the precision tabletop that we just talked about, 600 by 600. And then we have the modules. So everything that you saw in the simulation software has been replicated. We 3D printed all the parts, and then we put them in each position. I will show you that this is the module. This is a blank module. This one here, we have machined, and we can machine. So if you want to put your own robot on there, you can do that, or you want to build your own fixturing, we do have these available. Now, notice underneath you have the dowel pins. These dowel pins position themselves on the surface. So we can position it here, and we can flip it around. So we can face it north, south, east, or west. This provides great flexibility in moving the in adjusting maybe the robot position. Maybe we see the robot would probably work better over there, then we can shift it around. So there's configurability and reconfigurability. Also, you can reuse. So let's go ahead and run the application. It didn't glue it well enough. But we didn't put glue in here for obvious reasons for this demo. And that is the live demo of the gluing application. So what we're looking to achieve in this scenario here is an ROI, right? So a traditional robot cell engineering time, which includes mechanical design, electrical design, software design, drafting, procurement, soup to nuts. These are some numbers or rough numbers that we've come up with a calculation on that shows you kind of what your ROI first year would look like using a traditional robotic cell versus using kind of a modular system, a Tessella robotic cell. In what we've seen, it definitely reduces your NRE. It also gives you a better return on your investment, and that there's sustainability that's offered with that. There's also some connectorized enclosures that you can put with that too, to help with the full offering. And then this gives you an idea of what the standardized connectorized enclosure looks like. And that is pretty much of my demo. Is there any questions?
Hey, Thanks so much, Danny, for walking us through that. A couple questions that have come up. You had mentioned that you could get down to about a 20 micron repeatability. We've got a customer that has asked if you have seen the capability get down to a 10 micron repeatability.
So repeatability and precision is all based on kind of the capabilities of the machine shop that you're using. So the higher precision that you want, it's definitely possible. So yeah, we can definitely work with a higher precision machine, higher precision machine shop to be able to give you a higher precision plate.
Okay. Do you see your systems being used in just an electronics-based application or also maybe in a medical device application? And do you have the certifications to go into that medical device manufacturing?
So today we do not have the certifications for medical. The system is designed such that it can work within the medical. These are the industries that we are definitely targeting. They're smaller type lab applications is part of the offering. So it can be used in the medical. Today we do use it in electronics device manufacturing.
Okay. Is there a weight limit that you would recommend as to how, or a size limit on how large or heavy a part could be and still be compatible with your platform?
Our platform is rated for 500 pounds on the top. At 500 pounds, our deflection is, so the ratings that I showed you back here, let's jump back to this. So you'll see here, flatness, straightness and flatness spec, 100 microns, 600 millimeters across, right? That is our flatness spec. That is rated at a 500 pound load.
Okay. All right. And I think that's all the questions we've got that I see in the room this afternoon. So I want to thank you for taking the time, Danny, to walk us through the platform. This is definitely something that could make a precision robot cell, faster and less expensive to be able to get up and running. So I do appreciate the time you spent with us today. For our audience who's listening in, if you'd like some additional information, please check out the booth in the trade show area of the website today. Or if you're watching this on YouTube, please get in touch with us on our main website, which we're going to load into the comments when we upload this video, and we'll be happy to close the loop and touch base with you. Thanks again, Danny. I hope everyone has a great day.
Appreciate it.